Welcome to the next session of the lecture on rectangular waveguides. In this session, we are going to investigate the power flow in the waveguide, the characteristic impedance of the T and Tm modes in the waveguide, and the computation of power dissipation on the waveguide walls. Let us go to the lecture. So, we begin with the characteristic impedance of the T and Tm modes in the waveguide. So, let us write. So, let us begin with the characteristic impedances of the T and Tm modes in the waveguide. So, first let us consider the Tm to Z mode. So, we know the field equations for the Tm to Z mode. So, particularly if you look at equation 34a, we can obtain the electric field component E x, we can write it as 1 by, we can write it as E x is. So, particularly from equation 34a, we can find out the electric field component E x, and that is given by 1 by j omega epsilon minus j k z del psi del x, and that is using del psi del z as minus j k z psi, because the variation along the z direction of the psi function is assumed to be e to the power minus j k z z. So, minus j k z gets pulled out, and then we are left with the psi function for the differentiation of del psi del z. So, this can be written as minus k z by omega epsilon del psi del x, and that is k z by omega epsilon h y. Because minus del psi del x is h y. So, therefore, the characteristic impedance Z 0 m n for the Tm modes. So, therefore, the characteristic impedance Z 0 m n for the Tm to Z mode is given by E x by h y that is kz by omega epsilon, and that is beta by omega epsilon above the cutoff frequency f c, and that is equal to minus j alpha by omega epsilon for the frequency below the cutoff frequency. So, let us call this set of equation 50 in continuation with our previous set of equations. Now, we could compute the characteristic impedance in a different way. We could find out the characteristic impedance by considering the ratio of E y and H x, because E y and H x are also the transverse field components. So, let us see what happens if we consider the characteristic impedance as a ratio between E y and H x. So, E y is given by 1 by y cap del square psi del y del z, and H x is given by del psi del y, and therefore, we can write E y as 1 by j omega epsilon minus j k z times del psi del y, and that is equal to minus k z by epsilon, and that is equal to minus k z by omega epsilon H x. So, my z 0 m n T m becomes equal to minus E y by H x. Okay. So, this should be kept in mind that if I consider the different set of transverse components, the characteristic impedance changes its sign. So, therefore, in that sense the characteristic impedance is not uniquely defined with respect to the transverse components. Okay. So, this should be borne in mind for the waveguide structure. So, let us now go to the So, let us now go to the T to Z mode. We have in this case H y as 1 by j omega mu minus j k z times del psi del y, and that is equal to minus k z by omega mu del psi del y, and that is k z by omega mu E x. So, my z 0 m n t e is E x by H y it is omega mu by k z, and that is equal to omega mu by beta for the operating frequency greater than the cutoff frequency f c, and that is equal to omega mu by minus j alpha for the frequency lower than the cutoff frequency. So, we call this set equation 52. So, similar to the previous case, we can also quickly write that if I consider the ratio between E y and H x instead of E x and H y, how does the definition of characteristic impedance change, or how does the expression for characteristic impedance altered. So, E y is del psi by del x, H x is 1 by j omega mu del square psi del x del z, that is 1 by j omega mu minus j k z del psi del x that is minus k z by omega mu E y. Because del psi del x is E y. So, therefore, E y by H x becomes minus omega mu by k z, and that is equal to minus z 0 m n t e. So, in other words, z 0 m n t e becomes equal to minus E y by H x. So, we call this equation 53. So, we note again the change in sign due to taking the ratio between E y and H x. This phenomenon is similar to the T m to z mode. Now, let us go to the concept of power flow in the waveguide. So, when we are discussing the conservation of power, we encountered the power flow term, we encountered the Poynting vector, and we found that the integration of the Poynting vector over a surface gives the power flow through the surface. Okay. So, we use the same concept and apply it to the rectangular waveguide. So, let us consider the T to Z mode. The concept of the case of the T m to Z mode can be similarly obtained. So, we have S in bar as real part of S. We already interpreted these terms in the power conservation theorem, and that is real part of E cross H star. And therefore, power flow in the guide is double integral S dot d s, that is double integral real part of E cross H star dot dx dy. Now, E cross H star is nothing but u x u y u z E x E y E z H x H y H z, and that is u x E y H z star, expanding this cross product, minus E z H y star minus U y E x H z star minus E z H x star plus u z E x H y star minus E y minus E y H x star. Now, since for the T to Z mode we have E z equal to 0, since E z equal to 0, we have E cross H star equal to u x E y H z star minus u y E x H z star plus u z plus u z E x H y star minus E y H x star. So, therefore, for the power flow now, because I have the dot dx dy term or the dot ds term which is pointing along the u z direction, these two terms are not going to contribute to the power flow and this term only is going to contribute to the power flow. So, the power flow becomes, or the time average power flow is real part of 0 to b, 0 to a, E x h y star minus E y h x star dx dy. dy. So, here we are considering the waveguide cross section as before. So, this is my x axis, this is my y axis, this is my 0 to a is along the the a is along the x direction and the b dimension is along the y direction. So, if we now we have to write now if we substitute for E x h y and E y h x, we finally would obtain the expression for the time average power flow performing this integration and taking the real part. So, for that we consider the psi function for the T e to z mode. We know already that it is given by cos m pi x by a, cos n pi y by b, e to the power minus j k z z. A m n is the amplitude of the m nth mode. So, we know that E x is minus del psi del y, h y is 1 by z cap del square psi del y del z, E y is del psi del x and h x is 1 by z cap del square psi del x del z. So, therefore, after performing these operations on this psi function, so substituting this psi function here, here, here and here, and finally evaluating the integrand E x h y star minus E y h x star, we will obtain the power flow as real part of 0 to b, 0 to a, m n square n pi by b square cos square m pi x by a sin square n pi y by b e to the power minus j k z z k z by omega mu times e to the power plus j k z z This is because of the star, this is because of the star operation. So, therefore, it changes sign from e to the power minus j k z z to e to the power plus j k z z. So, this term and this term cancel out, and then we have the other term is minus and then we have the other term which is minus of minus a m n square m pi by a whole square sin square m pi x by a cos square n pi y by b e to the power minus j k z z times k z by omega mu e to the power plus j k z z, and then finally dx dy. So, again these two terms are as a result of change from the normal to the starred domain. So, therefore, the e to the power minus j k z z changes to e to the power plus j k z z, and therefore, these two cancel each other. And therefore, the power flow becomes a m n square k z by omega mu n pi by b square zero to b 0 to a cos square m pi x by a sin square n pi y by b dx dy plus m pi by a whole square zero to b 0 to a sin square m pi x by a cos square cos square n pi y by b dx dy. Now, the value of these integrals are please check yourself 0 to b 0 to a sin square m pi x by a cos square n pi y by b dx dy is b 0 to a cos square m pi x by a sin square n pi y by b dx dy. And that is a b by 4 if m and n are not 0. This integral 0 to b 0 to a cos square m pi x by a sin square n pi y by b dx dy is a b by 2 if m equal to 0 and n not equal to 0 and is 0 if n equal to 0. This integral 0 to b 0 to a sin square m pi x by a cos square n pi y by b dx dy is 0 for m equal to 0 and is a b by 2 for m not equal to 0 and n equal to 0. So, therefore, the time average power flow will be given by power flow in the T to Z Mn mode, that is P f tilde, that will be given by A m n square k z by omega mu n pi by b whole square plus m pi by a whole square times a b by 4 for n not equal to 0, m not equal to 0. Let us call this equation 54a, and it will be given by a m n square k z by omega mu n pi by b whole square plus m pi by a whole square whole square a b by 2 for n or m equal to 0. So, let us call this equation 54b. However, it is to be noted that if n modes are propagating simultaneously, the total power is the sum of the powers in the individual modes because of orthogonality. Okay. So, if n modes are propagating simultaneously in the waveguide, the total power is going to be the sum of the powers in the individual modes. Okay. So, let us stop here, we will continue.